All right, this is Physics 1A for section 1620 for April 2nd. Tonight what we're doing is we're going to be continuing to talk about energy and using energy to solve problems, and particularly this one over here to the right. So you can start reading it if you want to. And then we'll be talking about mechanical power. All right, let's get started. So just to refresh what we did last time. Last time what we did is we basically derived this relationship. The relationship that says that if I calculate the work done by non-conservative forces, that quantity, when there's work done on a system, should be equal to the change in kinetic energy of the system plus the change in potential energy of the system. And we said that you could break down potential energy into kind of two types for this class. One is the potential energy due to gravity, that's delta UG, and one is the potential energy due to springs. Each one of these has its own definition, right? So we know that, for example, the potential energy, the energy stored at a spring, is going to be equal to 1/2 a spring constant K multiplied by the amount that the spring is actually compressed, x squared. And the potential energy due to gravity is just the weight of an object, it's mg, right? That's the weight of an object, multiplied by its elevation above sea level. And this one will work as long as you don't get into outer space or something like that, where there's actually a more exact version of this that includes the mass of the Earth and the radius of the Earth and stuff like that. But we don't need to worry about that until we start talking about orbits. So for now, as long as we're close enough to the surface of the planet, this definition of the potential energy due to gravity will work. And then, of course, also you need to know kinetic energy. This should be something that you probably remember from your last physics class. We also derived it last time that kinetic energy is just 1/2 mass times velocity squared. And to calculate work, for work done in this class, there's a general expression that says that if we take the line integral of a force and you dot product it with the displacement, that'll give you the work. Of course, for a constant force, this often just ends up being work is equal to F dot delta R, where delta R is the displacement and F is the force, and the dot here represents that we're doing a scalar product or a dot product between the vectors. So that's what we learned last time, and we're going to use these ideas to solve this problem up here, problem number 6. On a thrill ride, a cart filled with people has a mass of 1,000 kilograms. It compresses a spring with a force constant of 45,000 newtons per meter. So let's start writing down the information we have right over here. So we know that the mass of our cart is given as 1,000 kilograms. And spring constant, that symbol is K that we used for that, is 45 kilonewtons, or 45,000 newtons per meter. And it compresses the spring by a distance of 2 meters. So that's going to be kind of like, this would be your x equal to 0 point. And the spring is compressed from that position. So our spring is basically like kind of like right here in this picture. And it normally would have been extended out to there, but now it's compressed by 2 meters. So I'm going to call that symbol x, and I'm actually going to call it x1. And that's going to be 2 meters. That's the spring compression to start with. There's an angle in the problem. We'll call that one theta. So we'll just say theta is equal to 30 degrees. And yeah, that's the only given information. Our question is, find the distance up the plane the cart stops, or will it go over the edge? So we're going to figure out how far will the cart actually go. You start off with a cart that has some energy stored up here. And, there's energy stored in this spring. And so if you let it go, the cart's going to zip off in that direction. And eventually, it's either going to go over the edge if it's going too fast, or it's going to come to stop somewhere along the ramp, right? And that's what we want to calculate, is how that works. Does anyone have any questions about the problem? So here's our ramp. And I'm going to draw the initial position here with our spring kind of wound up and say, okay, here's our equilibrium position for the spring. That's what we call x equal to 0 for the spring. That's the equilibrium position. And we've got our cart sitting right here, resting right against our spring. And we got people inside here too. That's our initial position. And then our final position, we're going to say, suppose some later time that the cart moves up the ramp. Okay, so it's going to be somewhere up along the ramp. And let's just assume that it comes to a stop at some point. Okay, if it doesn't, then what will happen is, we'll talk about that in a second. So we got our cart filled with people, and now the spring is going to be in the uncompressed state. It will have kind of be somewhere out here at x equal to 0. And yeah, that's our scenario. The key thing for solving problems involving this equation right here, and let's expand that equation out just a little bit more. Use a different color. So our equation basically states this. The work done by non-conservative forces is equal to the change in kinetic energy, so that's 1/2 mass. We need a change, so we need a velocity at another point and a velocity at our initial point. Okay, we'll label this as position 1, and we'll label this as position 2. Plus, we've also got change in potential energy due to gravity, so that's mg. That's going to be times y2 minus y1. And plus the spring, so 1/2 k, and that's going to be x2 squared minus x1 squared, right? So the thing you notice about this is hopefully that we have mass, that's given. We have k, that's given. Obviously g is given. Always what solving these problems ends up being about is just making sure that you kind of account for all the information you have, okay? So what I'm going to do is I'm just going to make a little box here and say we want to find x1, we want to find y1, we want to find v1. We want to know what all of these values are at this position, and then we want to do the same thing down here. We want to know what is x sub 2, what is y sub 2, and what is v2. These are basically little kind of diagrams that we just have to fill out to do these problems, right? So even if I know one of these values is 0, I'm still going to write it down like this because now I get to think about it. So I say, what is x1? Okay, that's going to be the initial compression of the spring, and that was given in the statement of the problem, right? Let's go down to v right here. If the cart just starts from rest, then the velocity here is going to be 0. And as far as y1 goes, well, we're basically free to choose really any point that we want for y equal to 0. So let's just go ahead and say that this point right here, we call that one y equal to 0. That would mean y1 would be 0. We're free to do that. And then let's make up the positive y direction as well. And we're done. 2, 0, and 0. Any questions about that? Yeah, before I drew the diagrams? That was a while ago. What was it talking about? Nice, dude. You guys are lucky having class at 6 p.m. right during prime time when the internet is the worst. I don't know. So did it cut out for like a long time? I can go back through and say what I said. So we've got, should I just go back through the problem in general? I can say a lot of things in 6 seconds. What was I trying to say? Sure. Okay. So just in general, strategy-wise on these problems, you need to draw a picture of the two situations, 1 and 2. And then for each situation, you want to label all the variables that you might have, right? And then, yeah, that's basically what I was saying. All right. So then next thing to do would be to take, to go ahead and fill out the same information down here at the bottom for x, y, and v down here. So for x2, this represent. Oh, I had another question. Why isn't y? I saw you said parallel. I thought you meant perpendicular to x. Okay, so it's really important you understand the following. Then, just to make sure this is clear, the quantity x in our 1/2 kx squared equation, this represents the compression of or the stretching of the string. Does that make sense? It's not a proper axis. I mean, it's an axis, but it always points parallel to the spring. It just represents, is the spring compressed or is it not compressed? Is there any energy stored in the spring? That's really the question that it answers. Does that answer your question, Shrek? Okay, cool. Yeah, in this case, they're not. I will also say, by the way, axes don't actually have to be perpendicular to each other. I don't know if you guys knew that, but you can have axes where they're like this. This could be x and this could be y. If you take a statics course, if any of you guys are going into engineering, you'll do this. You'll use axes that are not perpendicular to each other. Axes do not have to be perpendicular to each other. It just happens to be one of the easiest things to do in most situations, okay? I don't know if you guys knew that, but it's true. You go back and you read Descartes, you know, the Cartesian plane, Cartesian coordinate plane. You guys, that's like XY plane that we use. That coordinate plane, when Descartes first wrote these things down and started like defining what a coordinate plane was, he didn't use perpendicular axes. Like that came much, much later with modern textbooks that kind of obfuscate and mask the real truth. Anyway, whatever. So this is our equation. These are our values. We're going down here and we're plugging in x2, y2, and v2. Can x1 be negative? Sure, it can be negative, but it doesn't matter if it's positive or negative because you're squaring it. It would only matter if it was imaginary. Does that make sense? You're going to square it anyway, so it can be positive, it can be negative. It doesn't matter what it is. It just represents how much is the spring compressed. Okay, so what's x2 going to be? I spent all this time. It's the compression of the spring. How much is the spring compressed in the second situation? Can you guys answer that question? What's the compression of the spring? It's 0, exactly. That's right. What about y2? What's y2 going to be? Well, the blocks started kind of somewhere down here, right? That's where we were originally. And if we go over here to the right, it's so low on the screen, so it's hard to draw this. And we say this was our initial, that was our y equal to 0 point. Now the object is somewhere up here, right? And we can say y2 now, I would say is, if you look at this distance, whoops. If we call this distance right here to be d, I'm just going to call that distance d, then I would say y2 should be equal to something like this height right here, which would be not 2 sine 30, but just d sine 30. So 2 sine 30 was close, though. That would represent the elevation change. So 2 times the sine of 30, and I'm actually going to put theta here. I don't like writing numbers in. 2 sine 30 would be this height, right? That would be this height. That would be 2 sine 30. And then we need to add the additional length here. All right. So y2 is d sine theta. Put that in right there. And then what about v2? What would we put in for v2? What do we put in for this guy here? What's the velocity going to be at this point? You can read this sentence. Yeah, it's 0, because the card is either going to come to a stop or it's going to go over the edge. And we're kind of working off the idea that this is, that it's going to stop. Because if it stops, then the people don't fall off the edge, and if it doesn't stop in time, then they'll clearly fall into the pit with the hungry piranhas. They're hungry. Okay, so let's start plugging in numbers. I want to emphasize that every time you do one of these problems, you're going to be using this equation right here. And you need to do this. You need to make sure that you figure out all of these values here. I know this all looks messy, but I'm going to box off what we did. You need to figure out all of these values before you start using the equation. Quite often, a lot of those values will be 0, like v1 is 0, y1 is 0, x2 is 0, v2 also 0. Oh, look, this entire term was 0, right? Delta k was 0. It doesn't mean you don't need to write it down. In addition, there are no non-conservative forces acting here, although we're going to put some in the second part. We're going to do a part B to this where we'll put non-conservative forces in. So what's left? There's really just this term and that term. And so what I'm going to do is say, let's leave the mg. Here, I don't want to change colors too much. Let's go back to purple. So we'll leave the mg times y2 right here. I'm not going to plug anything in yet. And say that if we add 1/2 k times x1 squared, it'll show up over here. Right? And now we can plug in our values. So we know what this is. I want to rearrange a little bit here, but we're going to have 1/2 kx squared equals mg times d sine theta. All right. So now, if we want to solve for d, and the reason we would do that is because we want to figure out how far up the ramp it goes. That's going to be equal to 2 over mg sine theta. So then d is equal to, we can plug in the values. You guys can calculate it yourself now if you want to. So that's k x1 was 2 meters. And we're dividing all of that by 2 times the mass, which is 1,000. And then we multiply by g. And then times the sine of 30. Could just put a half in here, but I'll put sine 30 so nobody gets confused. And that's going to give us a value. We're going to use a different calculator tonight, one that doesn't suck. So using this calculator from EEWeb, in case you want to find this, I actually use this calculator to do homework and stuff because it's really good. All right, so we're calculating what D is, and it's so it's 45,000 times 4, and then we just need to divide by 2, divide by 1,000, divide by 9.8, divide by, I'm not going to divide by sine 30, we're going to divide by 0.5. And that's our answer, 18.4. We're going to change this a little bit, and I'm going to have you guys do a version of this. So that's where the people end up, and that's going to be somewhere like right about here. Because the total distance is 20 meters, that means they're not going to fall off. They will have already come to rest. All of their spring energy has been converted into gravitational energy. That's basically what that expression says, right? All the energy in the spring gets converted into gravitational energy. And then, yeah, we figure out how far up it goes, right? Okay, does that make sense? And do you guys have any... It doesn't matter whether G is positive or negative. No, sure it matters. G is always going to be positive. It's a positive number. When I write this here, this G will always be positive. When I say G, I'm always going to mean G equal to positive 9.8 meters per second squared. We've already taken into account the fact that it's negative in terms of when we worked out what happens with the work done by gravity. So you always going to put it, just put 9.8 in there, okay? Do you guys have any other questions? Yep. Yep. No. D, what I call D that we were solving for here, is the distance up the ramp that the object goes. And now if this number had been like 22, well then the cart would have gotten up to here and it would still have speed, so it would have, it would have fallen off the edge, right? Well, it would have gone into projectile motion, so it would have gone off like that and just like, Does that answer your question?
Yeah, I got it. Thank you.
No problem. Okay. So here's what I want you guys to do. We're going to do the same problem. Move this one down a lot. We're going to do the same problem. We're going to change the setup. So what I want you guys to try to do, and I'll give you like 5 minutes to do this, is say, suppose that we wanted to calculate, we'll call this part B. Suppose we wanted to figure out the exact amount of spring compression we need to make it so that our riders go right up to the edge, but don't fall off. Does that make sense? So the question is, what should the initial spring compression be? So to draw a picture of what I mean by that, so take our ramp. And let's say now that we've got our spring down here, right? And then this is equilibrium. That's x equal to 0. So the question would be, suppose that I put my cart right here. And I ask the question, what should this distance here be? Call it x1, right? That's what we've been calling it. So that later on, the cart basically gets right up to the edge and it comes to rest. So that's the question, what is x1 going to be now? So that the cart makes it all the way to the top and then comes to rest. Okay, and remember, if you look at the picture, this distance from here to here was 18 meters, if you look at the picture. right? So the equilibrium position was 18 meters away from the end. So it's 20 from the starting position here to here, but it started 2 meters back, right? So it's actually 18 meters then for the rest, and we're going to need that as part of the problem. So this distance here is 18 meters. And really, we need the cart to get right up to the edge, so I'm going to be a little bit silly about this, but we're going to take our cart here, and we'll lasso it. Whoops, I'll try to lasso it. Oops. See how much it's going to let me move it, just this part. Nope. Didn't catch it. Anyway, we want the cart to go right up to the very end. So we want the cart to basically be right up on the edge, like almost about to fall over. All the way to the end. Does the question make sense to you guys? Is that enough of a setup? Do you know what you need to do? You're obviously going to be using energy. You have a problem like this on your homework, and I just want to make sure you know how to do it before I send you off to do it. So take 5 minutes, 4 minutes, let's say. We'll start again at 6:30. Take some time to solve, and if you have any questions about the setup, let me know. Oh my god, I left something out. I wanted to put friction into this problem too. I'm very sorry. We need to do it too, because again, this is going to be part of the issue. Okay, whoops. So I'm going to change this. That means I'm going to give you guys more time. So we're going to let the coefficient of friction, I know it's rolling, but we're just going to treat it as if it's like sliding. And we're going to say this is the coefficient of kinetic friction, 0.1. I'm going to have to give you guys more time for this now. Sorry about that. I knew I forgot something. So add in friction as well, and let the coefficient of friction be 0.1. And then try to solve it. I'll give you guys 4 more minutes. I'm going to walk away for a second, though. If you get an answer for this, by the way, you can feel free to put it in the chat. I think you know what the answer is. This ink to text thing is really funny. 1.97 meters. It's going to have to be bigger than 2, right? I think it has to be bigger than 2. You're on the right order of magnitude then. That actually might be the answer. I just think that if it took 2 meters here, and that made it move a distance of 18.4 meters, and it would have needed to go 20 to get to the full distance, I think that the answer has to be greater than 2. In addition, if I add in friction, some of the energy is going to be lost due to friction, so again, you're going to need more energy to begin with. So, is that enough? 2.9 maybe? Let's see. Let's work it out. All right, let's see. I guess I have to ask you guys a couple questions here. Did you include the distance that the spring is compressed into the gravitational potential energy? Or did you just say, like, y final was 18 and y initial was 0? All right, it'd be 18 sine theta, right? Okay, let's see. All right, so we start this problem exactly as we did the last one. We just fill out our table, okay? Our possible values are x1, y1, v1. Initial velocity is 0. We can define the initial height to be 0, so that's what we'll do. We'll just define this point right here to be y equal to 0, so that's why y1 is going to be equal to 0. And we'll also indicate that down here. In this position, so there's our values. Can't emphasize enough that this is what these problems are about, is by getting those endpoints properly done. So we'll have x2, y2, and v2. Okay, and x2 is going to be 0 because the spring's not compressed. Y2 is going to be whatever this distance is here, right? Which I would say that distance would be equal to something like 18 meters plus x sub 1. Right there. Right, because it's x1 plus 18, right? So that means this side over here would be 18 meters plus x1 multiplied by the sine of theta. So that's our y2. Y2 is going to be 18 plus x1, and then times the sine of theta. And then v2 is going to be 0 because we want it to come to rest at the top. So now we can just write out our... Do those values make sense to everyone? And does anyone have any questions about that? Let's use this color. Here, the work done by non-conservative forces of this part is going to be the work done by the force of friction. The final kinetic energy and the initial kinetic energy are 0, so we can just say that this term is going to go to 0. For the potential energy due to gravity, that's going to be mg times y2 minus y1 plus this one, 1/2 k x2 squared minus x1 squared. The work done by friction. So to find work done by friction, we need to figure out what the force of friction is. And we can do that if we draw a free body diagram. We can say, okay, normal force goes this way, and the friction force points back this way. And then the weight goes straight down, where it makes an angle right here that we call theta, so that this vector here, which is the one we care about, would be mg cos theta. And we'd say that has to be equal to our normal force. And then for friction, we would say the work done by friction should be equal to the size of the friction force. So the friction force is going to be just equal to mu times this normal force right here. So it's going to be mu times mg cos theta. That's the force. We need to multiply by the distance the object travels. The distance the object travels is all the way this way. It's going to feel friction all along that surface. So we need the full 18 meters plus x1. And then you can't forget to do this part. It's also going to have to be multiplied by the angle between our displacement vector, which is this way. That's like our delta r, you might say. And the friction force, which is back this way. So the angle between these two is 180 degrees. So we also have to multiply by cosine 180. All that's going to be equal to the stuff on the right-hand side. And we can say that we know that we define y1 to be equal to 0. Could have sworn I just switched pins, but that's fine. And we also defined x2 to be equal to 0. So what we have is, on the right-hand side, mg times y2, and y2 is equal to this quantity here. So it's mg times 18 meters plus x1, and then times sine theta. Okay, that's our y2 right there. And then this is minus, zoom out just a little bit. We're going to shift this over just a little bit too. All right, so then minus 1/2 k times x1 squared. And that's ultimately what we're looking for there, is what x1 is equal to, right? All right. Does anyone have any questions? We're done with the physics stuff, so does anyone have any questions? Okay. We're now going to rearrange things a little bit. Cosine 180 is equal to -1. And what I'm going to try to do now is rearrange this to make it look like a quadratic formula. So we're going to get something like this. 0 is equal to, there is a -1/2 kx squared here. Put that one first. There's going to be some terms that are multiplied by x1. Okay, so I'm just going to write x1 times, there's a term that's mg sine theta. In fact, we're going to have mg on both of these. So it's going to be mg, and then you're going to have a sine theta from that term, and then you're going to have a mu cos theta. That's all the terms that are multiplied by x1. And there's also going to be a couple terms that are multiplied by 18. And they're going to be exactly the same. So it's going to be 18 meters times mg, and then multiplied by the same sine theta plus mu cos theta. And I think that's right. You guys can look at the algebra and make sure that it makes sense to you. Everything over here is negative, right? So when I move it to the right-hand side, it becomes positive. So like 18 times mu mg cos theta shows up right there. x1 times mu mg cos theta shows here. Z times x1. And then, yeah, so just grouping together terms. Make sure that you can follow the algebra there. I'll stop for a second. Does that make sense to you guys? Okay. This mg sine theta cos theta thing shows up twice. So we're going to calculate what it is real quick. So it's 18 times the mass, which was this. That's 18 times 1,000. And then times g, which is 9.8. We multiply that times, we'll open a parenthesis here, sine of theta. Theta is 30 degrees in this problem, so sine of theta is going to be 0.5 plus mu is 0.1. It's behind my thing here, but mu is 0.1 right there. And then we just multiply by cosine theta, so times the cosine of, make sure we're in degrees, 30 degrees. There we go. That, oh, you know what? I don't want to do 18 times this. I want to compute basically this quantity here, not that, this thing. So what we end up getting then, if we do that, is 5749, let's say. So this is, so our equation becomes something like this. So we have, this was 5749. The units would be newtons. And we could put the units on, why not? So newtons, that's times x1 plus. The other term is going to be the same thing times 18. So we take that and we multiply by 18. The last term is 103477. And the unit, I guess we can put the unit on this one too. The unit for this one is going to be joules, actually, because it's weight, which is in newtons, times meters, so Newton meters. So the unit there is going to be joules. And then the first term is 1/2 k, and I think k right here is 45,000, so this is going to be negative 22500, and that's times x1 whole squared. And now we have a quadratic we could do. I could even, let's erase this real quick. So this is 0. Sorry. So 0 equals -22500 x1 squared and then plus. Oh, that's what I was going to do. I was actually going to write the units in here. I'm being bad. Let's get this guy. Move over just a little bit. No, it didn't grab the other one. Right, whatever, I'll just rewrite it. Okay. What's the units on this one going to be? It's the units of K. It's like newtons per meter, right? So this one's going to be in units of newtons per meter. All of that times x1 squared plus this. Can anyone put that in a quadratic and tell me what the answer is? I'll do it and see how long it takes me. But if you get an answer, just put it in the chat for what the answers are here. So that's our equation. Is this the negative sign? This is the negative sign. Okay, so that gives me the negative root. And then if I redo it and I do the positive root, that's the answer I got, 2.3. Did anyone say 2.3? No. So I end up getting, oops, 2.3 meters or negative 2.0. Yeah, and it's going to be, this is going to be the answer. And it is slightly larger than 2, which is kind of what we expect, right? Did you guys follow that? Was it too much math? Did you get bored? Mm-hmm. So look at all the terms that have an x1 in them. This term has an x1, and this term has an x1, right? This term is multiplied by this. See how that's the same term? mg, and then mu cos theta. And it's negative on the left side, so it becomes positive on the right side, but that's times x1. On the right-hand side of the equation, we have x1 times sine theta times mg. x1, mg, sine theta. Does that make sense? Work the algebra out yourself, then. The -2. I mean, I can put another step in here, by the way, if you really want. And show how it came about. It's kind of sloppy, but yeah, just do the algebra yourself. And I think you'll be able to prove to yourself that this is true. Anyway, it's I can do it. I don't know that it'll make as much sense if you do it yourself, though, is mostly what I'm saying. I'll try to do them. If I use a finer pen, I can maybe fit it in here. Where'd the pen go? I lose this thing. Oh, there it is. Okay. Okay. I don't even know if I want to do this or not, but we'll do it. Left-hand side becomes Does that help you to see it? Because then we just, this term is times x1, and this term here is times x1. So I just factor them out. So oh, was my mic cutting out there? I wasn't talking while I wrote that. Yeah, that's the best part. You can't even tell when I'm intentionally not cueing my mic or when I am. It's just, anyway, that's what we've got. There's an argument to be made for just saying, like, not having class during this time and just having you guys watch the VODs because of the technical difficulties. Because it sounds like there's some pretty bad technical difficulties tonight. I don't know what you guys feel about that, but then you could just watch the, because this is the same lecture I gave yesterday, so you guys don't necessarily have to be here. I get that there's value in coming, because then of course you can directly ask questions and stuff, right? And that's extremely valuable. But anyway, I'll probably keep doing class. It's just the other video is, it's up there, right? It's on YouTube. It's exactly the same thing we're doing tonight. So if you are experiencing technical difficulties, you can always just go watch that one later, and I'll upload this one too. Any other questions about the problem we just did? It's kind of tricky, and I want to emphasize why it's tricky. It's because you need to include the distance that the spring is compressed in every single variable. Do you guys see that? Like, the distance that the spring was compressed showed up in the friction equation. It shows up in the potential energy for gravity equation, and it shows up in the potential energy due to the spring equation. And if you don't include it in every single place, you're going to get the problem wrong. And I know for a fact you have a problem that's exactly identical to what we did. It may even not have friction, I don't remember, but I know for a fact that it definitely includes this stuff. So, when you're doing that problem, it should be pretty obvious it's the same. I would say take some time to come back and review this at that time. Okay, so the next thing we want to do is to talk about power. And we're going to do one problem with power. So we're going to talk about power, and I'm going to do it with thicker ink. Power. So, a mechanical power is basically just this. It's the rate at which work is done by a system or on a system, or the rate at which energy is consumed. Rate of energy consumption. So to define that, then, there's two different ways we can do it. You can either define work divided by time. This would give you average power. Or it could also be equal to the change in mechanical energy in a system, the change in energy divided by the change in time. Just to remind you, when I say the letter E, I mean mechanical energy, which is kinetic plus potential energy, the sum of all those things. You can also define instantaneous power as being just kind of like the instantaneous rate at which work's being done, or the instantaneous change of the energy of a system. Either one of these can also be expressed in a nice way as well, where if we say that dW, which is the kind of differential amount of work, would be done by a force over some small displacement. And if we replace that in our equation right here, what we get is power is equal to F dot dr over dt. But then dr dt should be what? What is dr dt? What is dr dt? R represents position. The time rate of change of position is what? It's just velocity. So this ends up being F dot V. That's another way to describe instantaneous power. This one ends up being the most useful for the problem we're going to do next. I don't like salt. We'll just leave it like that and just underline it. So power is equal to force dot product with velocity. By the way, I just want to go back real quick. And someone asked the question, does it have any meaning, x1 equal to -2 meters? Like, what's the meaning of this right here? I think what that represents is if the spring had started already decompressed out to a certain point, no, it doesn't mean anything, actually, now that I think about it. It's just what the mathematics think the answer should be, but this is the only physically reasonable one. It doesn't actually mean anything in this case. So that's power. It's the rate at which energy is being used or done, and I can just describe it in a very simple way. Suppose you have two lawnmowers and you want to use both of them to mow lawn, okay? And one day you use a lawnmower that has 20 horsepower, and then 2 days later you use a lawnmower that has 40 horsepower. The idea would be that the 40 horsepower lawnmower is twice as powerful, so it can do the same lawn mowing in half the time. That's what we would think of as power, basically. Cars that have different power, have more ability to get from like 0 to 60. So if you get in a car like a Dodge Viper and it goes from 0 to 60 in like 3 seconds or something like that, that's probably ridiculous, but it's because the engine has a lot of power. Maybe it's like a 350 horsepower engine or something like that, right? But if you get into like, I don't know, like a Honda Civic and you try to accelerate from 0 to 60, it doesn't have as much power, so it can't turn the gas into mechanical energy as quickly. So it might take like 12 seconds to go from 0 to 60, if that makes sense. So when you hear a horsepower described for a car, it's talking about power. I should also mention one other thing here before we get started with this problem, which is units of power, shouldn't I? So we use two different units of power. So the units we use, there's actually 3 units, is the watt, and 1 watt, this is the thing you see on batteries and stuff like that, is equal to 1 joule per second. We also use horsepower. 1 horsepower, which is an older version that was originally, this name, horsepower, was supposed to be related to the power that a horse can pull. And this was the first, when James Watt, the guy that he didn't invent it, but the first guy that like really popularized steam engines and made them more commercially profitable. When he was trying to sell his steam engines, he was selling them to people that were like working on farms and were used to like horses doing things for you. And so he sold his steam engine by saying like, this steam engine can provide the power of like 20 horses. That's what they would say. And 1 horsepower is equal to 746 watts. And it's also equal to, in English units, so horsepower is its own unit in and of itself. It's not even English units. In English units, power would be described as foot-pounds per second. So 1 horsepower is 55 foot-pounds per second. Okay? Foot-pounds being work, and then seconds being time, obviously. So we're going to need these relationships right here, so we'll use those for the problem that we're going to do. All right, so here's our problem. A car engine has an output power of 20 horsepower when the car is traveling at a constant 55 feet per second on a level road. Find the average drag force on the car. That's the first thing we want to do. All right, so we've got a car, got a road. Okay, it's traveling along in this direction. It's moving with a constant speed, so its velocity is 55 feet per second. Okay, and we want to figure out the drag force. So we know that there's going to be some forces acting on this car, and let's just say the drag force acts backwards. Call it drag. We're going to say the force from the engine acts forwards. It's really the force of the engine on the drivetrain, which then acts on the axles and causes the wheels to turn, which then push off of the road with a friction force. But we're going to summarize all that action as just the force from the engine. The net forward force pushing the car forward. You're also going to have a normal force, and you're going to have a weight. And if the car is moving at constant speed, what does that mean about the sum of forces acting on the car? Is it equal to mass times the acceleration of the car? It would be. What's the acceleration of the car? What is the acceleration of a car that moves with a constant velocity? 0, that's right. So the net force has to be equal to 0, right? Which means that Fe minus d should be equal to 0, which means that the force from the engine is just going to be equal to the drag force. All right, now we have some information here. Let's start writing some stuff down. The engine has an output power of 20 horsepower. So I'm just going to call that the power of the engine and say it's equal to 20 horsepower. The car is traveling at a constant. We already defined that as v, and we want to find the drag force on the car. The equation we're going to want to use for this is the equation that relates power to velocity and force, because those are the things that were given in the problem. So I'm going to say that the power of the engine should be equal to the force of the engine multiplied by velocity. But then we know that the force of the engine is equal to the drag force, so that means that we can say the drag force is equal to the power of the engine divided by the velocity. So that's going to be 20 horsepower divided by 55 feet per second. But you might notice from above that horsepower and feet per second, they don't mesh. You need to make a conversion so that we can get the drag force in pounds. So we need to multiply this by a ratio of 1 horsepower being equal to 55, or it's not 55, I'm sorry, 550, my bad, 550 foot-pounds. Foot-pound per second. And then the units work out that you get something, I think this is going to be 200 pounds. That's equal to the drag force. Are you guys noticing my screen turned yellow? Does that actually show up? My screen like dims at 7 p.m. Okay, so it's just on my side. That's good. That would look bad on the... All right, so there we go. That's part A. Done. Questions? Part B says, if the drag force is proportional to the speed and the speed doubles, find the power needed. Drag force being proportional to velocity means that we can write an equation like this. Drag is equal to some constant. Maybe K is something like, we could call it the drag coefficient if you want to. The drag equals K times V. That's what that means. When it says drag is proportional to speed, that means you can make an equation. Drag is equal to the speed multiplied by some kind of proportionality constant. It's saying the speed doubles, so we're basically saying the velocity, we'll call it V2, is now 2 times the velocity in the first part, so 2 times 55. So 110 feet per second now. And we want to figure out the power needed. Now, there's 2 different ways that we can do this. The way that I think is the most simple is to make some kind of a ratio. We know that from our equation before that the drag force was equal to, well, let's put it this way. If we take the force of our engine and we multiply by the velocity, that was equal to the power. But we also know that the drag force is equal to the force from the engine, so we can just put kV in here, multiply by V, and that should be the power of the engine. The power of the engine, therefore, is K times V squared. Now, you could probably figure this out if you want to. If we knew that the power of the engine when it was 20 horsepower gave us a speed of 55 feet per second, and then we doubled the speed, what has to happen to the power? We doubled the speed, right? What has to happen to the power if we double the speed? Is it going to be double the power? 4 times the power? 8 times the power? Half the power? What do you guys think? We doubled the speed. What happens to the power? If the power is proportional to velocity squared. The power is proportional to velocity squared, and we doubled the velocity. What happens to the power? Grows. Yeah, it goes up by how much? Factor of 7? Factor of pi? 4 times as much. Exactly. Thank you. Factor of 4. Yeah, you guys got it. So actually, we kind of know what the answer should be. The answer should be 20 times 4. It should be 80 horsepower, right? Call it power 2. How can we see that? Well, I would say that if I know the power at one point in time, and I say that it's equal to K times the velocity at that point in time, and I divide this by the power at another point in time, then I get a ratio that tells me that P1 over P2, the ratio of the power, should be equal to V1 squared over V2 squared. Right? And now if we want to solve for power 2, we'll get that P2 should be equal to P1 multiplied by V2 squared over V1 squared. But since V2 is double V1, this is just equal to 4 times power 1. And you can plug in numbers if you want. You can plug in V2 equal to 110. You can plug in V1 equal to, we'll call this one V1 equal to 55, and you'll get the same answer. And power 1 was, so it's 4 times 20. So exactly as you guys said, the answer power 2 is equal to 4 times as much, or 80 horsepower. Does that make sense? Now, there's another way we could have done it. We could have actually just solved for K, right? So if we take p power 1 and we divide by velocity 1 squared, that gives us the value of k. So power 1 was 20 horsepower, and v1 was 55 feet per second. We'd have to square that. And that would give us the value for k. We'd also probably need to convert the horsepower to get a reasonable version of this, although we don't really have to do this, by multiplying by 1 horsepower, and then here 550 foot-pounds per second, and then we could solve for what k is. I think we might need this for the last part. We don't need this for the last part, but you could. This is another way you could do it. So we would find that if we take 20 times 550 and we divide by 55 twice, we get 3.63. So this would mean that our constant, our drag coefficient would be it's actually 3.64. What are the units? So there's a foot per second and a foot per second. I think it's pounds divided by feet per second or something like that. Because one of the feet per second cancel. You have a feet per second in the denominator, the HP's cancel. Yeah, I think this is the unit. Pounds per foot per second. Anyone have any questions? The last part says, if the maximum engine output is 150 horsepower, find the maximum speed of the car. Now this is really easy if we use this method right here. So if we say P1 over P max has to be equal to V1 over V max squared. And if we know max power is 150 horsepower, then we can solve this very easily for the velocity. We're going to get V max squared should be equal to P max over P1 times V1 whole squared. So it's going to be equal to the square root, So then V max should be equal to the square root of P max divided by P1, and then that multiplied by V1, not inside the square root. So P max is 150 horsepower. P1, we could choose either the answer from part 1 or part 2. We'll use the one for part 1. God, I can't write when it gets this far. HP, and then V1, which was, I think, 55 feet per second. So we get V max is equal to 1530. Square root of 7.5 is going to be like pretty close to, no, I don't know what that is. All right, 150 divided by 20. 2.73 times 55. 151 feet per second. There we go. Do you guys have any questions? How to do power? We might do one more power problem next time, and then we'll move into the next chapter, which I guess is momentum, I think. Probably what we'll be doing next week. But that's all for tonight. Do you guys have any questions before I close down the recording?